All right, how's it going, everyone? Back for computer vision stuff. So this is the same slide as last time. You guys are still working on your final projects. Still have the poster session. All of those things still apply. Any random questions about things? Is that a question? You can. What is you have a final at 4 p.m.? Shouldn't. This is your final project. This is like your final time. But okay. Yeah, this is supposed to be the final exam period for the class. Yeah. It is in the atrium. Yeah, that should be somewhere, but it's not on this slide. It's probably on the website. Any other random questions? Cool. All right. What did we talk about last time? I don't even remember. We'll find out. We talked about doing object detection, and we talked about basically the YOLO method of object detection, which was this sort of different approach where we're going to use just one pass through a neural network to predict all of the detected objects for an image. So we have our neural network here. We put in an image, we process it. What we get out is this tensor, and this tensor is going to encode basically all of the bounding boxes and class probabilities for an image. So it's going to have some stuff about the bounding box, like if the bounding box contains an object and how big the bounding box is. It's also going to have these class probabilities that say, if there is an object, what is the object in this bounding box? And so what this looks like is basically we think about these different regions of the image, and this tensor is encoding basically the probability that there's an object. So for this cell, it does contain an object. It has this little car in it. For like this cell, it would predict 0 because there isn't an object in that cell of the image. It's going to predict this bounding box that'll look something like this. And we're going to predict class probabilities for all of these locations as well, which may end up kind of looking like sort of a coarse segmentation map. And so we're going to sort of combine all of these together, and we get basically a bunch of bounding boxes weighted by their class probabilities. And now we have sort of a few prominent bounding boxes when we actually run this at test time, and then a bunch of background stuff. And so we do our standard sort of thresholding and non-max suppression to get rid of duplicate detections and to only basically have the most prominent detections at the end. We talked about basically different encoding schemes for these bounding boxes. We can try to predict sort of the width and height and XY coordinates directly, or we can have basically some easier method of doing this prediction. The idea behind using sort of these bounding box priors or anchor boxes you'll see in other literature is basically making the prediction easier for the network. Basically, the easier you make these predictions for the neural network to be, a neural network can kind of learn any arbitrary function, but if you make the function easier for it to learn, it will basically perform better, and it will use up less of its kind of computational power on learning the easy stuff, like predicting the bounding box, and maybe it'll use more of that for doing some of the harder tasks, like classifying the difference between like a dog or a bear or a cat, which all are kind of these furry little objects. So how we're going to make bounding box prediction easier is basically we have these priors that we sort of specify ahead of time, these p's. And if we're predicting sort of an offset from this prior, we're basically predicting some terms tx, ty, tw, and th. And the way that we figure out basically the actual bounding box that we've predicted is doing some kind of transformation on these terms. So in general, you're basically taking this prior bounding box and predicting some small change in terms of the width and in terms of the height. And you're also probably predicting some kind of offset in terms of the xy coordinates of something. In this case, the offset we're going to predict is basically we have this cell location that we're looking at currently. We're going to predict the xy offset from basically the top left corner of this cell. So cx and cy are sort of the offsets of the current location that we're looking. And then we're going to predict tx and ty, and when we take a sigmoid transform of tx and ty, we get the offsets that we shift sort of in from the top left corner of this cell to predict this particular bounding box. And there are a bunch of different ways of doing bounding box encodings, and they all have sort of their pluses and minuses. So this is just the way that YOLO currently does bounding box prediction. It's fairly similar to the way that like faster RCNN does bounding box prediction, which is also fairly similar to the way that RFCN, all of these different methods have started to slowly kind of converge on different norms and patterns, but there's still some space out there for kind of getting the right one. And if you shift these around, it doesn't end up affecting the performance by too much, but we're sort of battling over a couple percentage points. So these are the things that people have kind of converged on. So we talked about the loss function for YOLO, which is this combination of loss based on sort of the bounding box localization error based on the confidence. So this is the probability of an object in a given location, and the classification score. So if there is an object, what is that object? And we have different types of losses for each of these different components based on what we're sort of trying to optimize for. And we're basically just feeding images through this network, calculating some loss, and doing kind of the standard backpropagation that you guys have implemented for tuning the network to predict the thing that we basically want it to predict. And because we're doing this, we don't really have to think about like how we do each of these individual components or like what things kind of matter. All we're sort of tuning is like these different trade-offs between these different terms to affect the end result of our network. It means that we don't have like as much kind of control over exactly how the network is processing these images, but in practice we kind of don't really want that much control. We want the network to do all of the learning for us, basically. And this is kind of why neural networks are so cool in doing these computer vision tasks, because we don't have to do these like long extended pipelines of like do this to the image and then extract these things and then do this stuff. Now we can just kind of throw everything into a neural network, figure out what a good loss function is, and if you basically give it enough training data, the neural network will be able to learn the task that you want it to do, probably. We talked about sort of all of the different methods and all of these improvements that people have been doing, and RCNN, and sort of the successors to RCNN, fast and faster RCNN, for basically improving the prediction speed and also improving the accuracy. So the big thing with RCNN, if you remember, is you extract all of these different regions, and then you run those regions through a convolutional network and predict basically the bounding box and class probabilities for each of those regions. And this involves basically taking all of these subregions and running them through a neural network independently, which takes a really long time. So we talked about basically a different way of doing that, and one of the components that we'll need is this idea of ROI Align, where basically if we have some feature map and we have some region that's some sub-window of that feature map, we may want to basically take some sub-window of this feature map and scale it to some standard size. And the idea with this is basically we're going to take some little window that we're looking at, and maybe the thing that we want to end up with is a 2x2 feature map that represents some subregion of this larger feature map. So what we're going to do is basically split this window up into a 2x2 grid and calculate basically 1 pixel for each of these 4 spatial locations. And then we're going to calculate some basically subpixels within each of these larger pixels of our eventual feature map. We're going to do bilinear interpolation from the original feature map to figure out what the value of these subpixels are. And then we're going to do some pooling operation on these subpixels to figure out what the value for this entire area should be. And that pooling could be max pooling or average pooling or something. And this is sort of the idea behind ROI Align, which allows us to take sort of an arbitrary feature map and some region within that arbitrary feature map and project it into this fixed size. So you can do this operation with any basically size of window in this feature map, and you'll always end up with a 2x2 feature map as output of this ROI Align operation. So fast RCNN uses this idea of doing ROI Align or ROI pooling, and we're going to run our convolutional net just first on the entire image. We're going to take our region proposals and project them onto this feature map. We're going to do ROI Align or ROI pooling to take this projection and project it to a standard sort of size. So all of these are going to be 2 by 2 or 4 by 4. Even though all of these regions of interest might be totally different sizes, now we have some standard size that we can feed into some neural network or some linear layer and use this linear layer or neural network to predict the same things that we wanted to predict before. So our class probabilities and our bounding box coordinates. And this is cool because now instead of having thousands of times where we have to run this convolutional network, we only have to run it once, and we can do this ROI pooling so that we still have to run this sort of subnetwork like a couple thousand times maybe for an image, but it's a lot less work than running this whole thing down here. Now we run into this problem of we're still using selective search, which takes a long time to produce these regions of interest for an image. So instead, with faster RCNN, we're basically going to do it all with this neural network where we take our feature map, we have some linear layers or something that basically produced some bounding box proposals. So they predict sort of similar to what YOLO is doing, a bunch of possible bounding boxes. And then we can take these possible bounding boxes, look at the feature map, do ROI pooling, and then do the same thing that we were doing before with running our final layers of doing classification and sort of this fixing these bounding box offset prediction stuffs. And we talked about how a lot of these methods started basically saturating the Pascal data set. So people have started switching to this new data set, COCO, which is common objects in context. It's much bigger. It's got a lot more stuff going on. It also has this cool property of basically segmentation masks for all of the objects. So instead of just a bounding box around these people, we actually have this fine-grained pixel level labeling of both, this pixel is a sheep, but also it belongs to this particular sheep and isn't, part of any of these other instances of sheep. So on COCO, you can sort of see some different numbers for a bunch of these different methods. And we see that we sort of get this nice trade-off between speed and accuracy, where we have sort of faster, less accurate methods over here. And there's some kind of curve that seems like it's getting defined for more and more accurate methods kind of up in this region of the image. But the important thing here is we're still sitting in kind of the mid-30s in terms of average precision. This has since moved up to sort of the low 40s, basically. But still, on the COCO data set, we have a huge room for improvement, which is pretty cool because we haven't kind of saturated this data set completely. There's a lot of things that we still have left to learn about doing object detection. And then we talked about basically we have semantic segmentation with pixel level labels. We have object detection where we're putting bounding boxes around different instances. Why don't we combine these together into instance segmentation? So basically, given an image, produce the same kind of labels that the COCO data set already has. Basically, pixel level labelings of both what class does this pixel belong to and what instance does it belong to. So all of the pixels in this car that are sort of labeled green over here, they're all labeled car, but they're also labeled with this instance of car as distinct from sort of these other instances of car that might appear in this image. And we talked about one approach for this is mask RCNN, where basically we have our same object detector that we had before, this faster RCNN network, and we can just kind of stick on it after we do our ROI pooling, this little mask prediction mechanism. So this is for any region of interest that we extract out of here. This is just going to predict a little 14 by 14 mask, and then we can sort of take that 14 by 14 mask that we predict and basically upsample it back to whatever size our actual region is. So if our region happens to be sort of a lot taller than it is wide, for example, we might predict a 14 by 14 mask, and then we can just resize that mask back up to, I don't know what size this person is, 128 by 512 or something. And this is actually the output from mask RCNN. You can see it works pretty well. There's still some sort of pixels where it doesn't quite work out, or kind of it doesn't get the boundary conditions quite right. But in practice, this is a pretty cool algorithm for you guys to know about. Mask RCNN, since it has this extra kind of, so we have sort of this extra thing that we're adding on to faster RCNN, our object detector that we were talking about. And we actually get a little bit more information because now we're trying to do this mask prediction task as well. So it turns out that when we kind of train this entire thing, when we add on this mask prediction, it actually learns better features in these previous layers and causes the network to also be better at doing object detection. So this is kind of an interesting phenomenon where basically if you add more signal into your machine learning algorithm, you can end up actually learning better representations. And when you learn better representations in your feature extractor, you end up actually becoming better at other tasks that aren't necessarily the task that you're sort of caring about or the task that you added on, this mask prediction. But adding on mask prediction actually gets us to be better at object detection as well. So mask RCNN is up in the 40s somewhere in terms of mean average precision just on detection. So on predicting bounding boxes is actually better than a lot of these other techniques. But it takes about half a second, I think, per image. So it's a fair amount slower than some of these other techniques, but you know, a little bit more accurate. So depending on what you care about, you might want to make those trade-offs between different methods. How are people feeling about object detection, instance segmentation, question? Yeah.
So does that
So you need to, yeah, so the whole point of ROI Align is you have to feed these things into a neural network at some point. And the inputs and outputs of a neural network are generally fixed in size. So these regions of interest that you're looking at in this feature map could be sort of arbitrarily sized. You have to project them to some standard size so that you can actually feed them into the final layers that are going to be doing the bounding box prediction and the class probability prediction.
So if you
wouldn't. You can't. Yeah, that's why you have to use it. Yeah.
So I have a question about
Yeah.
but
Yeah. Yeah, this is sort of a data set dependent thing. Different data sets decide to do this different ways. So like Coco has basically picked these 80 objects and they've labeled them. There is a data set called Visual Genome that has basically taken the Coco data set and added a bunch of subcategories. So I think in that data set they start adding parts to things, like they would label potentially like headlights versus the rest of the car versus you know, even specific kinds of car, sedans versus coupes or whatever. I don't really know my cars very well, but it all kind of depends on what people. So a lot of these data sets aren't actually meant to be kind of the data set that you actually care about if you're like deploying some of these in practice. They're just meant to be benchmarks for how well can you make models that kind of process this type of information. So in practice, if the thing that you really cared about was like detecting car license plates, for example, what you would want to do is go out and get a bunch of data and label it with car license plates. And then you could go back to a data set like this and look at the models that performed well on a data set like this. And you can kind of assume that if it performs well on this data set, then it will perform well on your data set because this data set has, you know, a bunch of different categories and a bunch of different things. And so you would basically, you know, this is kind of a benchmark, so you would find the good models on that, and then you would take them and port them over to your new data set or train them on your new data set. And that's kind of the general like thought for what should be going on with these data sets. They're not meant to be sort of like the be-all, end-all of visual data. It's more like if a model performs well on these kind of data sets, it will hopefully perform well on sort of arbitrary other kinds of data. So now we're going to switch gears a little bit and talk about language and vision. So a cool thing about the Coco data set is that this data set also has these captions, which we kind of touched on a little bit last time, but we might have an image that looks like this, and during the labeling process, they basically had a bunch of people write out what was going on in the image. So in this case, one of the captions was, "The man at bat readies to swing at the pitch while the umpire looks on." And these are just random people on Mechanical Turk. So it's just like you get 5 sentences per image, and they're not necessarily like the best sentences. This sentence is like a little bit weird. "The man at bat readies to swing at the pitch while the umpire looks on." But it's like, it gives you some idea of what's going on. And now that we have sort of these captions, you might be thinking to yourself, like, maybe we can train some model on these images and have them predict these captions. And the idea behind this is, like, we've been talking about these other tasks of like image classification and object detection, segmentation. A lot of these tasks seem like they're sort of just pattern matching. Like if you want to find a car, you're just looking for some pattern of pixels that sort of looks like a car. Or if you want to find a bike, you're looking for some pattern of pixels that looks like a bike. But for example, in this image here, there's no pitcher and there's no like ball getting thrown to the pitcher or anything, or to the batter. You're just kind of like looking at this image, and as a person, you know what's going on. You know that this person is playing baseball, and they're like getting ready, so there must be a pitcher somewhere else who's going to throw a ball at this person, otherwise they'd be kind of silly for just standing there like that. And so for predicting these captions, you both have to kind of process some information about what's going on in the image, but you also have to sort of understand the image at a little bit deeper level, basically. You can't just sort of look for the individual components. You have to kind of form some coherent picture of what's happening in the image and maybe even like why it's happening and things like that. So one idea is basically like, maybe instead of doing object detection or image classification or something, maybe we should focus on trying to predict captions for images, because if you could predict a really good caption for an image, maybe that means that your algorithm is kind of doing some real understanding of the image, or really actually like knows what's going on, is processing it at some deeper level. So people got really excited when the COCO dataset came out and they started working on how you would kind of do this. And to do this, we basically have to combine these two different components together, because now we have language, but we also have this visual information. And language has sort of this time component where we have sequences of words, and the words only really mean anything once you string them together in some kind of sequence. And so what we really want to do now is model sort of this sequential or time series data. And since we've been talking about neural networks and how great they are the whole time, one thing you might be asking is, like, how can we model this process using neural networks? So if you see a sentence like this, as you're reading this sentence, you can kind of predict, if there's some blank space, you're reading along, you're like a long time ago in a blank, from sort of the context, we can look at the nearby words in this sentence and say, well, this is probably galaxy, because we're all Star Wars fans here. I just saw the new Star Wars movie. Yeah, it's good. I liked it. Really? Do not at me. I know a lot of people don't like it. But if we sort of, if we kind of think about this problem of like, how do we go from this string here with some blank information in this string, how would we think about basically predicting this word? One thing you might think about doing is basically, well, let's train some neural network, and our input to it will be basically some string, and our output will be the word that will come next in this string. So a long time ago in A, and then our output would basically be whatever the next word is that we wanted it to be. And the problem with this is basically our encoding of this input. And in particular, there are like a million words in the English language. It turns out there are like somewhere around 3,000 words will get you like 95% of most text, I think. So that means like 5% of the time you'll hit some word that you don't know as you're reading through text. 95% is pretty good. Obviously, this is some long-tail distribution. So I think in practice, people generally use around 10,000 words or more when they're doing some kind of encoding into a neural network. But the problem is, like, if we want our input to this neural network to be just a string of words, like, how long of a string do you want? If we're looking at just encodings of 6-word strings, then we basically have, like 3,000 words times the 6 words that we're going to feed into this neural network, and we'll have basically this 18,000 long input vector, and that's basically just for words that have strings that have exactly 6 words in them. And then maybe you want to feed in some sentence that has 7 words or some sentence that has 8 words, and you want to predict the next word. How would you go about doing that? We basically have, again, this problem where neural networks, by sort of design, have to have some fixed size input and some fixed size output. And what we really want is basically some model where we can feed in some variable-sized thing and then predict potentially also some variable-sized thing as well. So this is the naive approach for a reason. You shouldn't do things this way. And what we're actually going to do is use recurrent neural networks. And the idea behind these recurrent neural networks is that we're going to read one token or one thing at a time. So a token could be a word, it could be a character, it could be some other way of dividing up the sentence. I think it's possible that people use things like syllables for doing this as well, especially with speech data. People talk about basically short chunks of speech. But we're going to read one token at a time. We're going to process that token. We're potentially going to produce some kind of output. But we're also going to update what we think of as basically our internal memory or some internal state in the network. So when we start out, basically, our hidden layer is just going to kind of depend on whatever our first input is that we get into the network. But at subsequent time steps, we're going to take this internal state of the network, and we're going to sort of propagate it forward so that at the next time step, we have this hidden layer where it depends both on the input to the neural network, but also on the previous hidden layer, or also on the previous kind of state of the network. And we can think of this as basically being some kind of memory that we have. So for running this neural network, we have some update rule to our memory that depends on our input, but we're also going to have some update rule that depends on what the memory was at the previous time step. So as we read through this sentence, it says a long time, and when we process time, we are going to make some update to our memory, but we also just read the word long, and so maybe we have some memory in here that gets forward propagated, and instead of just thinking of time as, for example, being a verb, one sense of using the word time is like to time how long something takes. Because we have this word long that comes before, we have some kind of state that exists in our memory. And when we forward propagate that here, we can hopefully resolve the ambiguity between this word time, whether we mean sort of the verb or the noun. And when we process sort of these two words together and we propagate this memory forward in time, we'll be able to resolve some of these things and hopefully model kind of these dependencies between words that happen over this sequence. And so now basically the question is, like, we have this model, and we basically have a situation where we have some kind of internal state of this network. And the internal state of the network is going to depend on the input, and it's also going to depend on the previous internal state. And we're going to use that state to produce some kind of output. And generally, you can think of this whole thing as just kind of one recurrent block. And you can stack multiple of these on top of each other to make a larger neural network if you wanted, or you can just have sort of a single recurrent block if you want. And we have a couple things to think about now. So we have this update rule where, and an important thing is you could think about basically these updates between these different layers as potentially depending on when you're performing the update. So maybe, early on in reading your sentence, you have some way of updating your internal memory. And maybe as you read sort of later on in your sentence, you have some different method of updating your internal memory. And we're going to sort of assume that that isn't the case, and that basically this update rule stays static over time. So as we're reading this sentence, we're not kind of changing the rules of how we're updating our memory, although our previous memory can affect sort of what our next internal state is going to be. But basically, the rules of how that happens aren't time dependent. So we're going to use the same update function over time to take our previous memory and our input to determine what our current memory or current internal state is. So one thing that we have to figure out is basically how do we want to do this update rule? So how do we want our current state to depend on our past state? And also, how do we want our input to affect our memory? How do we want this update rule to happen where we're taking in some new input? We should also probably update our internal state based on that as well. a sentence isn't just defined by all the words that came before, it also matters what word you're sort of currently reading. So we have to figure out basically these two different components, how we're going to process input, how our previous state is going to affect our current state, and then given sort of all of these things, our input, our memory, how are we going to produce our output? And there are a bunch of different ways of doing this, and these form sort of different kinds of RNNs that people talk about. So the sort of simplest way of doing this are these vanilla RNNs, where we have some pretty simple processes taking place. So what we're basically going to do is we have our input xt, we have our previous memory h at t minus 1, and we want to produce some output yt. So what we have to do is basically first calculate some new memory or some new internal state. And what we're going to do looks a lot like the operations that we've been doing in the past. So we're going to have some weight matrix w, and we're going to multiply it by xt. We're also going to have some weight matrix v, and we're going to multiply it by ht minus 1. And so these are just the standard neural network layers that you guys are used to from the past, where we have some fully connected layer. We have some weight matrix that is the size of the input by the size of the output. When we multiply this weight matrix by the input, we get some vector that is the size of the output. So we have these two weight matrices, and we have our input and our internal state. So each of these will produce some vector. Those vectors will be the same length. And then all we have to do is just add those vectors together. And again, it's a neural network, so you often want some kind of activation function phi here. And this update rule will basically produce our new internal state at time t. And with a vanilla RNN, the output that we're going to use for y at time t is just going to be the same as our internal state. So there's actually no difference between sort of the memory that we're keeping around and the output that we're going to produce. And this is just sort of one way of doing RNNs, but so the output is just going to be the same as our current memory state. And before I show you guys that, let's talk about these different matrices that we have here. So who can tell me just very quickly what W does? Yeah. Yeah. What role does it sort of play in the processing, I guess? Yeah. And what does V do? Yeah, and some, well, I guess I already told you guys what phi was. I explained this too fast. Exactly, so we have sort of W and V, which are these weight matrices. One of them takes the input and updates the memory. The other one takes the previous memory and forms updates to the current one. We're just going to sort of add those two updates together, and we have some activation function phi. And in practice, we don't really have to do these kind of things independently. Since we're just adding together basically the outputs of Wx and Vh, we could actually just form this as a single fully connected network where we've appended these two streams together. So if we think about basically appending x at time t and our internal state h at time t minus 1, those are just two vectors. And if we just kind of mash them together, then we can form one big matrix W, which will essentially be mashing together the two matrices W and V from the previous slide. And now we have a single set of weights that can take our input, and we're going to apply them, just matrix multiply them as we were doing with our fully connected networks before. And we have some activation function phi. So in this little example, this is just a tan h function. So we have our input x at time t. It comes in and gets appended to our previous output from the previous time step, h at t minus 1. We append those together, apply some matrix operation with our weight w, and then apply some activation function. And the output that we get here will be both the output to this recurrent block, and will also be the state that we sort of propagate forward to the next time step. Now, there's a problem with kind of doing it this way, and the problem stems from the fact that basically our internal state at time t depends on our previous internal state, but it's also sort of this big operation that we're doing. And basically at every time step, we're going to be recomputing our internal state, or our memory, totally from scratch. So we have basically this previous internal state, h at time t minus 1, but then we're multiplying it by all of these weights. We're applying some activation function on top of it. There's nothing really constraining like our previous internal state or our previous memory to be very similar to the memory that we're going to produce next. And this is a problem for basically remembering things for a long time. So if we're reading some sentence, or if we're reading, for a book, for example, there are going to be characters that are introduced in that book in the first couple chapters, and later on, you're going to have to sort of keep around a lot of that state. You're going to have to remember who these characters are, what sort of their motivations are, things about them, and these long-term dependencies can happen sort of over arbitrary distances. So one thing you might think about is like, after we read every single word, we might not want to do this like complete and total update to our memory where we're kind of calculating our new memory from scratch. What we might want to do is some basically incremental update to our memory, kind of like how a computer operates, right? So if you have a computer and you're running some program, at every time step, or after it like processes a single instruction, it doesn't wipe the memory totally clean and have some update rule to basically write in all new memory. What it actually does is basically changes some small portion of the memory, but leaves most of it the same, because if you just read sort of a single word, or if you did sort of just a single instruction, the actual things that you have to remember haven't changed that much most of the time. So the idea is basically to add in some kind of gating functionality. And what this gating functionality is going to do is we have our internal memory and we have some new input. We want to basically decide what portions of memory are important for predicting the output. And we also want to decide what portions of memory are good to keep around and what portions of memory can be overwritten. And if some of the memory can be overwritten, we have to figure out what we want to write into that location instead. And so there are actually like a bunch of different ways that people have come up with doing these sort of gated RNNs. We are going to talk about the sort of most popular are GRUs and LSTMs. We'll talk about what they mean in a second. I'm going to go in depth into how GRUs work. LSTMs are very similar and actually predate GRUs. GRUs are sort of a simpler version of them. LSTMs are more complicated and harder to explain, so we're not going to talk about them. But before we had this picture of what kind of these vanilla RNNs look like, this is what a GRU, or a gated recurrent unit, looks like. And so we still have this same thing where basically we have this input of x at time t. We have some state that gets, or memory that gets passed from the previous time step, h at time t minus 1. And we just have a bunch of processing that's going on in here. And again, we're doing the same thing. We're producing some outputs. We're going to produce some output h at times t. And we're also going to produce basically the same internal state or memory and send it to sort of the next block in this chain. And we have a bunch of different equations for figuring out what this output and internal state updates are going to be. And we're just going to talk about them sort of in order. And the basic idea for what's going on is at every time step, we're going to look at our memory and our input and decide what parts of the memory are important. So for example, we had these two possible instances of the word time. And maybe as we kind of read longer in the sentence, we discover that, oh, time instead of a verb in this sense, it actually meant a noun. So maybe we can overwrite the part of the memory that was kind of looking at the word time as a verb instead of a noun, or as a noun instead of a verb. Once we've kind of done that disambiguation, some of this memory becomes important, and some of this memory becomes less important. So we're going to decide which pieces of our memory are important, and using those important pieces of our memory and using this new input, we're going to calculate some update to make to our memory. And then we're also going to decide which parts of our memory to keep around and which parts of them to update. These two things may seem like they're kind of redundant. That's because they are a little bit redundant, but don't worry about it. So we're going to decide which parts of our memory basically to update and which parts to throw away. And then we're going to output some new memory that is going to be the parts of the old memory that we kept around, plus the parts of this update that we calculated, but just for the pieces of memory that we decided we could throw away. So if there were some portions of memory that we decided we didn't need anymore, we're going to figure out where that corresponds in this update that we calculated and just pull those into this new memory that we're forming. And that's going to be our output, is basically this weighted sum of our old memory and the important parts of it versus the new memory and the important parts of the new memory. So the important things to know about in this GRU model. The first is this reset gate, which basically when we have some input and we have our old memory, what the reset gate is going to do is just figure out what parts of the memory to pay attention to, what parts are sort of important as we're processing this input x at time t. So we calculate R, which is going to be this sigmoid or logistic, this logistic function that depends on basically our previous state and our previous input, or sorry, our previous state and our current input. We're going to learn some separate weights for this reset gate. And we remember that sort of this logistic function is going to output some number that's between 1 and 0, basically. And the idea is really we want our reset gate to be 1 for the important parts of the memory to think about when we process these input, and it should be 0 for the parts of memory that are irrelevant to processing whatever this next word is in our sentence that we're looking at. And then when we calculate h tilde, we are going to use our reset gate to modify our previous internal state. So R is just going to be some numbers 1 or 0, or potentially somewhere in between. And what this will end up doing is basically keeping around portions of our previous state that we think are important and throwing away portions of the previous state that may not be important for making this update. And so we're going to calculate this update, h tilde, which, again, we're using tan h here, but this could be any potential activation function. It doesn't really matter. These sigmoids, or these logistics, are actually important because we want them to be between 0 and 1. But this activation could potentially be anything. But this update is basically going to be based on our input at time t, xt, and also this kind of modified memory from previous, where we've zeroed out the portions of memory that we've decided aren't necessarily important. And all we're kind of keeping around are the portions of memory that we think are important for updating this, for making these updates, or for calculating basically some new memory h tilde. But h tilde isn't actually going to be the thing that we output directly. H tilde is basically going to be some proposed changes to our memory. And now we have to figure out basically which of those proposed changes we want to keep and which things in the old memory we want to keep from h at time t minus 1. And so to do that, we're going to use this update gate. And this update gate is basically going to calculate this value z, which, again, we're doing this logistic function applied to, again, sort of a fully connected layer, or these weights multiplied by appending our input to our previous state. And so we can think about this as basically trying to process or figure out which parts of our previous memory are important, which parts should we keep around, and which parts can we just kind of throw out or get rid of. And what we end up doing with this z is multiplying it by sort of multiplying either it by our updates that we've proposed h tilde, or multiplying 1 minus it by the previous state that we had. So basically, when z is 1, we are going to take as output sort of the specific parts of memory from our update. And if z is 1, we're going to ignore what our previous memory was for a particular location. And if z is 0, we are not going to take any components from this new update that we calculated h tilde. We're going to take that entire section of memory from our previous internal state, or our previous memory, h of t minus 1. And so z is just kind of this weighting function, or this trade-off between what parts matter from our old internal state or our old memory, and what parts should we update with our new h tilde that we calculated. So our final output, h at time t, is just going to be this weighted sum based on our update gate z, and it's going to be a weighted sum between the previous output and this new kind of potential output h tilde that we calculated. And so that's kind of the whole part of gated recurrent units. And again, this is just sort of one building block, or one, you can think of this as kind of taking the place of like a fully connected layer or a convolutional layer in a neural network, in that this is one piece that you can then kind of stack on top of each other. And these things can potentially have different sizes. They can have different input and output sizes. They can have different sizes for their internal state. But this is kind of the general rules for processing these GRUs over time. Do people have questions about how these GRUs work? Or, yeah? Huh? So this can go at a bunch of places in your network. It kind of depends on what you want to be doing. In a language model, generally you will just like stack a few of these on top of each other, like 3 or 4 or something. And then this will produce some kind of output, basically. But the output that it's producing in this case is also kind of the same as the internal state that it's kind of keeping around, or its internal memory. So you may additionally want to do some extra processing on top of that that isn't necessarily time dependent. So what a lot of people do is basically use these RNN blocks, or use like GRUs or LSTMs, to process an input sentence and produce some representation. And then they use like a fully connected layer on top of that representation to produce the final output. So to produce, for example, the word or the character that you're looking at. Does that make a little bit of sense? And then we have LSTMs, which are long short-term memory networks. I don't understand what long short-term memory is, but we won't worry about it too much. And it's a little bit more complicated than GRUs. And like I said, we're not going to go into the details of all of this stuff. But basically, we see a lot of kind of the same things happening, where we have a bunch of internal state that's using these logistic functions. And then we are basically doing some element-wise multiplication of some of these things that we've calculated with some things that depend on basically the previous internal state and also the output of the previous layer, et cetera. So in this case, actually, as we're moving forward through time, we are forward propagating between each module both the output of the previous module and also some internal state that doesn't get outputted at all, these C's, C at time t-1 and C at time t. And the basic idea here is just like these LSTMs look fairly similar to what GRUs have going on. We have this same kind of thing where basically instead of recalculating our complete updates to our internal memory or to our output every time, we're just going to look at some of our internal memory and keep a lot of it around and only make updates to some of it. And so, like we were talking about before, basically we had this big problem where it was hard to model these long-term dependencies if we're doing this full weight update, or doing this full memory update every time we process some new input. And now with these GRUs or with these LSTMs, what we have is a much longer term memory that we can keep around, basically. Because we're only sort of updating portions of it at a time, we have these longer term dependencies that can just kind of arise naturally that are much harder to get when we're doing these full updates. And this actually helps with training a lot, because if you sort of use these vanilla RNNs, and you can imagine sort of unrolling this through time and then trying to train it to predict something. So for example, say that you wanted to read in this sentence, and you wanted to predict sort of this last output away, so a long time ago in a galaxy far, far away. the value that you might get for this word away, or for whatever sort of the last word that you might want to predict is, depends on basically all of these, all of the words that kind of came in the sentence previously. But if we have basically this memory update that modifies the memory completely at every time step, it's really hard to get this long-term dependence. And because of that, we fall victim to the same problems that we were falling victim to with really large convolutional neural networks, where we have this gradient vanishing that happens, where we have some error that's going to be associated with our prediction at this time step. And what we want to do is backpropagate that error, both to sort of the both to kind of the weights that depend on the input, but also we want to backpropagate that error through this network over time. So we want to basically modify both kind of processing rules, the processing rules that take into account the input and also the processing rules that take into account the previous memory. We want to backpropagate error through both of these channels and figure out how to modify those update rules so that we can better predict this output. But with kind of these naive methods of doing this internal state update, it's really hard to backpropagate this error very far, because as we talked about, a lot of times these memories don't really have very much dependence on each other. And you know, this basically can be seen as like a really deep neural network where we don't have any kind of special rules in place. Like we talked about, residual networks were one way of combating vanishing gradient problem in convolutional networks. LSTMs and GRUs are a way that we can calculate this vanishing gradient problem in these recurrent neural networks where we're processing this time series data. So because we are sort of keeping around most of our internal state most of the time, it provides our gradient this really clear path to backpropagate through until that internal state actually was created by something in the input. And then we have some way of basically backpropagating our gradient through this network over time and fixing our update rules and fixing sort of the rules that change the internal state based on what our input is. And this is like a really sort of core component of LSTMs and GRUs, so are people pretty comfortable with like why these things are important and why they're solving a problem that is important to solve? Cool. So there are a couple different tasks that we can perform with these neural networks. A really common one is language modeling. So all we're going to do is basically read in streams of characters and try to predict what the next character is. So for example, we're just going to read in, you know, like some really long text or anything. And after we read in every word, we're going to try to predict what the next word in the sentence is. So this is an example of our network basically getting everything right. But the idea is we're going to read in the word A. And without kind of reading anything else, we're going to have to predict what the next word is. In this case, it's long. And then we are going to forward propagate our network through time and read in the next character or the next word, which might be long. And then our network should predict basically what the word is after that. And it might be time, et cetera. So what we end up getting is this network where the expected output is just going to kind of be the expected input, but shifted through time by one, basically. And this is a really common way that people in NLP think about basically modeling language, is can you read a string of characters and figure out, or can you read a string of words and figure out what the next word is going to be? Does this problem setup sort of make sense for people? For why this is kind of modeling how, at least in some sense, how a language works. This makes some assumptions that basically like you can read like half of a sentence and predict what the next half of a sentence, or at least what the next word is going to be, which you're not necessarily able to like predict exactly what that word is, but oftentimes you can predict some distribution over what kind of the next possible words are going to be. And that's why people in NLP sort of think about this model as being good for modeling language. And if we're kind of good at this, we can model language well. So, oh, I lost it. OK. So one interesting thing that you can do, let me just switch back. So one interesting thing that you can do with a model like this after you've trained it is you can just feed in some word or some character here, and the model will make some prediction. And you can take whatever word it predicts and feed it in as input again, and the model will make some new prediction. And you can take that output and feed it into the model again and make some new prediction. And by doing this, you basically have a generative model that once you've trained it on a bunch of language, you can take it and run it and have it generate sentences just kind of on its own. And again, we talked about how this is like a hard problem to basically predict what the next word in some sentence is going to be. But what we end up with is a model that sort of will just kind of say gibberish at you, basically. But the gibberish is sometimes sort of intelligible. So I have a GRU model that's trained on, oh, I killed it. So this is a GRU model trained on a bunch of news articles, I think. So I can't remember what the data set is, just a bunch of textual data taken from the internet. So now we can just kind of run it, and it's basically seeded with a couple new line characters. And then it will just kind of start predicting text and feeding that text back into itself on its own and predicting what the next text should be. So we have that it just kind of like, so here's sort of a little artifact. This is clearly supposed to be a news article from the AP. So I think this is pulling from a bunch of different sources, but one of them is text data from news articles. So it says things that kind of, sort of, sometimes make sense. But once you actually like kind of read the whole sentence, there's not really a lot of semantic meaning. But like the Armed Services Authority said the crisis was just a popular sports community, which is a world new consumer research security system. So like that doesn't really make any sense, but like there's some little things in there that start kind of making sense. Since the settlement includes the South Carolina, the conservatives suggest that he was serious in kind of scare quotes, it looks like, and bound into the road to a half decade, but he was designed to win. So there's obviously some kind of political stuff that's included in this data set as well. The interesting thing about this model is that it's actually trained, we were talking before about models trained on a word level. This is a model trained on a character level. So it's actually looking at individual characters at a time and trying to predict what the next character will be. So apart from just kind of forming coherent sentences, this model also, for example, has to learn how to spell things correctly. So it's actually like learned that pretty well. But there's nothing, for example, constraining the model when it's printed out like ALASK. There's nothing that makes it predict A as the next character. It's just kind of learned over time that that's how you spell a word, and that it should basically in general try to spell these things correctly. This one is really weird. No state official said it was Alaska's death in Sweden. That's not good. But we can also, so if we scroll up basically a little bit, we can see what the actual model is that we're using. And in particular, we're using basically 3 GRU layers. So our input, again, is characters. So it's just one of 256 bytes, basically. And we're going to input some character, and we're going to run it through this model. This model, basically, all of these GRU layers are going to have a vector input of size 256. They're going to output a vector of size 256. These connected layers that you see in between are just the connections that we talked about for these update gates, reset gates, and doing this update prediction. The reason that there are 6 of them instead of 3 is because I don't do the concatenation together of the input and the previous state. I just process each of them independently and then sum the vectors together. But this model basically has these 3 GRU layers, and then this final GRU layer will produce some kind of output that is some representation, and then we have this final connected layer that basically takes that representation and predicts some distribution, and we're going to run a softmax over it. And again, this is just going to be some byte somewhere between 0 and 255, basically, and we can take that byte and turn it into what sort of the character value of it is, and we're going to output a bunch of characters. Now, the cool thing, again, is that this was trained on a bunch of just random text scraped from the internet, but we can train it on just kind of any textual data that we want. So let's see what other ones I have in here. So I took the same model and trained it basically on the Bible multiple times. And we see that, before it was talking about sort of these news stories. Now it's talking about like a lot of biblical things. There's a lot of God and Lord in there. Again, it's saying things that like almost parse or almost sort of make semantic sense, but don't quite. Then said I that wisdom that is for my kingdom shall be saved. Now he said, let him live, and that glory in his brother, that he may not be wrought for the wicked, etc. So like a bunch of random things going on. Let's see, I scraped a bunch of Trump tweets, and we can predict sort of things that Trump might tweet out about. I will be interviewed by @GOP, by Megyn Kelly on the New York Times, of the Arab League. Who knows? Honestly, like, not too far off base in terms of how much they make sense. And then, Shakespeare is fun, so you can train this on a bunch of Shakespeare plays, and you get a bunch of lines that characters might say, and then also like stage directions. Sometimes the stage directions are in English, and sometimes they're not. In general, one thing that this model isn't quite good at is keeping the same characters around over time. So usually like a scene will just involve a bunch of different characters. Like Achilles is in here, but then King Henry V, and then this clown and Angelo. But none of these characters kind of stay the same over time, but they do say things. My lord will approve the most just heart to see your royal servant of his bed. I don't know. But, just like kind of seeing these and sort of seeing these models actually basically predict some sentences, you can see that like they're kind of learning something. And again, this is all on a character level. So if you actually do this on a word level, they work a lot better because they don't basically have to learn how to spell on their own. They can devote more of kind of their processing to combining together words in ways that make sense. Question?
Looking at a character level, then
Yeah.
words might be.
Exactly. It has to do all of, it has to learn to put in spaces to divide up words, and it has to then like think about patterns that it's seen before in terms of where those spaces occur and like trying to figure, yeah, exactly. So there's a lot of processing that we're kind of making, when we're doing it on a character level, there's a lot of processing that we're making the network do. The advantage of doing a character-based model is it's a lot more general. So if you think about doing a word-based model, you have to actually figure out what words you're going to put into your vocabulary. And anytime you see a word that's not in your vocabulary, you can't really do anything with it. And you also can't predict words that aren't in your vocabulary. So your model will never kind of, for example, if the input to your model is some sentence that mentions some new person that you've never heard of before, and maybe the output that you want is also to mention that person again, a word-based model would never be able to sort of handle predicting that person's name again because it doesn't have that in its vocabulary, whereas a character-based model, at least in theory, could, although training it to be able to do that is another sort of challenge. But do we have a question? Yeah. Yeah, I have this trained, but not for this particular model, so it would take me a while to find it again. But you can basically predict, so that's one cool thing that I did was just feed it in like a bunch of random textual data, and because Unicode just uses these same bytes but has sort of special bytes for saying that characters are longer or not longer, you can train a model that will basically predict correct Unicode characters, and then will just like predict text data that is written in like well-formed UTF-8 basically. So you can feed in just kind of arbitrary data to these character models, and it'll just kind of predict it. Since UTF-8 is sort of handled doing the correct encoding for us, basically. I think that it would be very hard to do. Like, again, there are some things that you can learn with these models and some things that are sort of impossible to learn. And like decrypting stuff is one of those things that may just kind of be impossible. Like, you know, theoretically, like information theoretic-wise, it's supposed to be very hard to do that. So I think that that would be basically impossible. Yeah. No, so the input might be like a period or a comma or something, and maybe it's learned that like sometimes when it sees a period, and after it's written out or after it's read in, you know, some number of other words or characters, like maybe that phrase is over and you have to go on to the next line or something. So again, these are all kind of things that it just learns over time. So yeah, it's outputting like all the new line characters. It's doing all of the formatting with like it's putting square brackets around stuff and everything. OK, so going back to our slides. Language modeling, pretty cool. You can do some fun stuff with it. Another thing that you can do is translation or question answering. So now we're going to take basically the same model that we had before, and we're going to basically ignore the output for some of the model and ignore the input for some of the model. But basically, we're going to input basically some string of words or characters, and then we basically want to train the network to output that same string or sets of characters, but in potentially a different language. Or potentially what we want to feed in is a question, and we want the model to output the answer to that question. So we might input hola, ¿cómo estás? And what we want is hello, how are you? To be sort of the output of some translation model. And this should kind of feel a little bit familiar to you guys. This is an example of basically using an encoder and decoder network, similar to what we were doing with semantic segmentation, where basically we have this encoder that's going to take in some sentence, and it's going to produce basically some representation of that sentence, some encoding. And then all that's getting transferred over to the decoder network is this encoding or this memory that our encoder network has built up for us. And what the decoder network is going to do is take this encoding and process it and output some stream of characters or words that should be some correct decoding of that. In this case, we're decoding, you know, from Spanish to English, but you could also imagine that our encoding, if we ask the network a question like, what is 2 plus 5, hopefully the encoding will perform some kind of representation to say basically what the question was, and then our output network will basically do some kind of processing. We'll hopefully output the number 7 or something along those lines. So you can think of this kind of model as being useful both for like translation tasks, but also for question answering tasks potentially, or for a bunch of different things, kind of this encoder-decoder architecture. So how does this all relate to vision? One thing that we could potentially do, since we have some encoding that we're creating, and we have some decoder network that will take this encoding and produce some sentences output, we can imagine basically our encoder network, instead of using some text input, let's just use an image. And we will basically feed our image into some convolutional neural network. We'll produce some feature map at the end. And then let's just take that feature map and say that that's our encoding of our image. And we can feed that encoding into this decoder and train our decoder to output some sentence. And now that we basically have our COCO data set, we have a bunch of pairs of images and sentences. So we can train this a bunch by just feeding in images and forcing basically our decoder network to predict the caption for that particular image. And we have sort of this unified network architecture, right, where this is all just one big neural network. We talked about, you know, all of the different components of neural networks that basically go into this decoder network. And so now we're going to basically generate some sentence. We have some sentence that we wanted our decoder to generate, so we can calculate some loss or some loss function for the sort of encoded, or the actual sentence that we produced versus the sentence that we wanted to produce. And then we can calculate our error and backpropagate it all the way through time, through this entire recurrent neural network, and then backpropagate it backward all the way through our convolutional neural network as well. So we can update all of these weights in both the convolutional network and our decoder to basically produce better sentences, or to produce the sentence that we actually wanted when we feed in a particular image. And by doing this, sort of train the entire system to perform this task of image captioning. And one thing that you might be asking yourself is basically, how does it know when to stop? Usually there is some stop token and also potentially even a start token that you output. So basically you would run your decoder network until it output a particular stop token. You could use kind of anything, but usually, like, if you're doing a character model, you might do 0. If you're doing a word model, you might insert a special token that is just like an end of sentence token or something. So you would basically just take your state that was calculated by the encoder, run the neural network until you produce the stop token, and then everything before that token is the sentence that you kind of generated. And so in practice, the COCO dataset came out like 2014 or something. And there was one conference that year where like 7 people all did the exact same thing. They just like did this like encoder decoder style thing for image captioning, and the people running the conference were like, what do we do with all of this? Like, we got a bunch of papers that are all basically identical. They let them all in because they all kind of came up with it independently, basically. But this was like this really exciting thing that people got really into, because we had now this data set, and basically people did kind of the most obvious thing to start doing some of this image captioning, but in practice it kind of sort of started to work. So here are some examples of different images and their caption, and it sort of works. So a group of people standing around a room with remotes. They're a group of people kind of holding Wiimotes. A young boy is holding a baseball bat. That's basically what's happening. A cow. Let me get my little thing back so I can read this in here. A cow is standing in the middle of a street. Yeah, that checks out. A cat is sitting on a toilet seat. That's kind of funny. It's like a little cat sitting on a toilet seat. Display case filled with different kind of donuts, etc. Sometimes the models didn't work completely correctly. So a man standing next to a clock on the wall. Well, there's a man standing next to a clock. It's not on the wall. A young boy is holding a baseball bat. Not quite. And that would be a very young boy. A cat is sitting on a couch with a remote control. Well, it's something sitting on a couch with a remote control. I like this one, a baby laying on bed with a teddy bear. It's like that guy clearly has like a pronounced beard. So, in situations like this, you can sort of see what the network was looking at. It's just like not quite all the way there, basically. And then sometimes it just kind of goes totally off the rails, basically. I really like this one, a horse standing in the middle of a road. Like, there is no horse in that picture. A woman holding a teddy bear in front of a mirror. Like, there's no mirror or teddy bear in this picture. This one is funny because this is clearly like a bathroom where the toilet was removed, but it says a toilet with a seat up in a bathroom, but really there's just no actual toilet there. So our image captioning models are definitely learning something. It's kind of hard to figure out what exactly is going on. And this paper came along and basically said, OK, instead of doing captioning, what if we just found the closest image in our training data and just predicted that caption directly? And it turns out that that actually works about as well as a lot of these methods were working, just doing kind of this nearest neighbor problem. So what these CNNs and RNNs were actually basically learning was just memorize all of the captions in our training data, and when we see a new image, just more or less predict the closest caption from the data that we've seen in our training data. It turns out that modern captioning algorithms, which are a little bit more complex than this, actually can do some kind of interesting things. they can actually sort of predict these like visual details that aren't necessarily like strictly from the training data. And they're starting to generalize basically a little bit better. But this is definitely one example of basically seeing our methods overfit to the training data and not sort of generalizing well to new situations where the new situation is, you know, a picture of a street where there isn't a horse standing in the middle of it, I guess. And one really hard thing actually about image captioning is just how do we score it? And in general, you know, it's really hard to get computers to come up with captions for an image. So how do we figure out how good a caption is when we've generated it for an image? Now, the most obvious way is you have a human read that caption, and the human can pretty easily tell, like, these are bad captions for these images. But in practice, when we're actually like running these large-scale competitions and we have tens of thousands of images, it's really hard to get a human to go through and score all of them manually. So we've come up with all of these different automated scoring techniques, like Blue and Meteor and Cider and all of these things. And in practice, basically, these automated scoring methods have a lot of issues with them as well. So, here's a couple more examples of captioning. This is, again, from one of sort of the original papers. So it's not always basically totally correct, but several people are on a dock in the water. These are like 5 generated captions. Some people on a boat in the harbor. That one worked pretty well. The women are drinking wine in the kitchen. A woman is taking a picture of wine. A woman taking a picture of a wine glass. Like, you can see that basically a lot of these captions start to be very similar. Like, clearly there's some image in the training set where there was a woman taking a picture of a wine glass. That's definitely not what's happening in this image. You can kind of scroll through and see a woman is looking down on a skateboard. A woman who is sitting on a skateboard. She is leaning on a skateboard with a girl. Like, there's none of that is kind of happening in this image. So there are some images where it sort of works and some images where it doesn't. I fed this into, I think this is like Microsoft's captioning algorithm. It said, I think it's a dog sitting on a bicycle. Not quite correct. But the interesting thing sort of about these automated scoring methods, so we have all these automated scoring methods like Cider and Meteor and Blue and stuff. And these are sort of the top image captioning algorithms according to these metrics right now. And if we scroll down for a while, there's nearest neighbor. So nearest neighbor is not super good. Here's human. So if you have a human write a caption for your image, according to these automated scoring metrics, they come in like far, far below the state of the art. So let's do that scroll one more time. And so in particular, there was one time where they actually had a bunch of humans score the output of these instead of having these automated methods do it. And the humans, when you ask humans to score them, are just way better, right? So like 63% pass this, like, the test I think in this case was, do you think this caption is as good as a caption that would be generated by a human? And when you ask people that about human-generated captions, 63% of the time they say that those captions are as good or better than captions generated by humans. If you ask that about some of the top scoring methods, they say that like 25-ish% of the time. So there's this really clear gap that you get when you're doing scoring based on what humans think. But when you use any of these automated scoring methods for doing this, humans end up really far down on the list, basically. And that's because all of these automated scoring methods, all they can do is basically look at the ground truth captions and see how close, by some metrics, those ground truth captions are with the generated caption. And in practice, humans have basically some variability where humans will describe an image different kinds of ways. And so those generally don't score super well according to these automated metrics, but they actually make a lot more sense when you look at these things. So it turns out that captioning is just kind of a hard problem to do well, and also just a really hard problem to score well. Which means that basically maybe image captioning isn't kind of the right thing to be looking at. Maybe we should be looking at some other problems that are potentially easier to know if we're like doing the right thing on. And also it seems like basically image captioning, the things that work well are just kind of these nearest neighbor approaches. So one thing that you might think about next is basically visual question answering. So this is very similar to captioning in that we're basically combining together an image and some textual data. So for example, we have this image of this person, and we have this question, what is the mustache made of? And our system has to process both this image and the text, and also output some text on its own as the answer of this. And one idea is that hopefully this requires a little bit more understanding to do well on. So instead of just predicting some kind of like nearest neighbor caption, it's really hard to do that with question answering because the question actually matters. You can't just predict banana for all of these questions because the question might be like how many people are in this image, or it might be what color hair does the woman have. And for each of these different questions, you have to understand the image in sort of a different way. But it's way easier to evaluate visual question answering models because you either get the question right or you don't get it right, and you can start doing kind of these accuracy level calculations. So just for the last demo, I'll just show you guys this little visual question answering thing. So you can try out your own images, and I'll try to do that. But do we have any? We had a last minute question. Do you have a question?